Maybe this type of name Hilbert transform is present in the unit which contains Fourier transform, but it doesn't mean that like it is performing some transformation directly. It is not changing the domain. Hilbert transform basically is a phase shifter. Its function is shifting phase, and Hilbert transform is specifically a constant phase shifter, and that is plus or minus pi by 2 phase shift. So why we are talking about all this Hilbert transform or phase shifting concept here? Because in the example of a real world signal communications, so if I am talking about a transmitter which is transmitting signals into the free space, and the free space consists of so many obstacles in the form of buildings or in the form of trees, in the form of the leaves of a tree, in the form of raindrops. If any, all these are the obstacles for the signal to get deteriorated or to experience a change in pace. So what I'll do to compensate that at the receiver, I perform some operation of phase shifting so that I can compensate whatever the phase shift the signal experiences throughout this free space. And this is one of the example where I'll be using this Hilbert transform at the receiver when the receiver signal is experiencing a phase shift of plus or minus pi. Is it clear?
Yes, sir.
Right. This is the reason we are using this Hilbert transform. And these phase shifters, generally in the case of communications, we call them as equalizers. That you will come across in analog communication case. So now directly going into the Hilbert transform mathematical concept. So Hilbert transform basically an LTI system that you can check it later after that, because it is performing or transforming the phase shift. I'm rating it as Hilbert transformer. It's not like the transformer you are thinking about. It is about a phase shifter. Okay. Now, if I give input x of t to the Hilbert transformer, which is a plus or minus 90 degrees or pi by 2 phase shift, it performs only phase shift. So what I'm doing is I'm representing the output of the Hilbert transform as x cap. Input is x and output of the Hilbert transform is x cap. Now I have a question. Will be able to understand this phase shift easily in time domain or frequency domain?
Frequency domain.
Generally, we talk about the word phase only in the frequency domain, not in the time domain. So time domain, maybe we see the result in time domain directly, but all this phase shift concept, whatever we are going to see, will be explained only in the frequency domain. So if I want to do all this explanation in frequency domain, I definitely have to use the Fourier transform. Okay. So now, if this Hilbert transformer impulse response is represented by h of t, now output is convolution between input and impulse response. Accepted for an LTI system?
Yes, sir.
output from an LTI system is a convolution between input and impulse response. Okay, so we have to have a knowledge on how h of t can be obtained. So that's why I am now trying to explain you some concept here. Let's see it here. How can I represent Fourier transform of x of t? X of omega. Am I right?
Yes, sir. Yes, sir.
Okay. Fourier transform of x of t is x of omega. First, suppose if I want to show that x of t has experienced phase shift by amount of plus or minus pi by 2, then how can I show? I can show only in the frequency domain. That means x of omega can be represented in its polar form like this. And when I multiply this with e power of plus or minus j pi by 2, then mod x of omega e power of j theta of omega into e power of plus or minus j pi by 2. Do you understand what I am going to say? X of omega in its polar form represented like this, having magnitude and phase. If this x of t is being sent to the Hilbert transformer, then definitely it experiences a phase shift by an amount of plus or minus pi by 2. So that means since phase shift is properly explained in frequency domain, that's why I am multiplying the input spectrum with e power of plus or minus j pi by 2. And since x of omega is written in its polar form like this remains as it is. Now, do you think there is any change in the magnitude response? If I multiply with e power of plus or minus j pi by 2, do you think there is a change in the magnitude response?
No, sir.
No, sir.
No. So you can have only a shift in phase. By how much amount? Plus or minus pi by 2. Now, do you understand how this shift occurred? Is this the shift plus or minus pi by 2 what I am talking about? Understood? The phase is shifted by either plus or minus. Okay? Got my point?
Yes, sir.
Yes, sir.
Okay. Yes, sir. Now see here. So output is x of t convolution h of t. I want to check or represent that in its frequency domain. It becomes multiplication. Okay. Now, can you please compare these two, this product and this product? Can you compare?
Yes, sir.
Now, can you please tell me what is h of omega?
E power plus or minus j pi by 2.
Exactly. E power of plus or minus j pi by 2. And tell me what is this h of omega now? What is h of omega now? H of omega is now the Hilbert transform. Got my point?
Yes, sir. Yes, sir.
Okay. So that is how. So all this, there is no need to write all this in the examination. This is only for your understanding. Like, how can we explain the concept of phase shift in frequency domain? So, input spectrum multiplied with e power of plus or minus j pi by 2 results in a shift in phase by plus or minus pi by 2. And that function should be performed by Hilbert transform. That's why comparing these two with this one, h of omega takes a definition of e power of plus or minus j pi by 2. Okay. Now, I am now writing the frequency response representation of Hilbert transform. So Hilbert transformer frequency response h of omega. Tell me, it can be either e power of j minus j pi by 2 or it can be e power of j pi by 2. Am I right?
Yes, sir.
And this is for positive frequencies it does, and this is for negative frequencies it does. So this is how the frequency response of Hilbert transform is defined. Magnitude is 1 since it is performing only the phase shift. That's why I'm writing only like this. Okay, just for your understanding and rubbing this one. E power of minus j pi by 2. Is it like cos pi by 2 minus j sin pi by 2?
Yes, sir.
What is its value? What is its value?
Minus J.
Minus j. Now what is e power of j pi by 2?
J.
Right, it is j. Okay, so what I am doing is, instead of having two definitions for positive frequencies and negative frequencies, I am representing this with a single definition. It is h of omega equal to minus j signal function of omega. Please try to understand how this is true. Anyone can explain? What is signal function? It is 1 for positive frequencies and minus 1 for negative frequencies. Am I right?
Yes,
Do you remember this signal function?
Yes, sir.
yes, sir.
Okay. So for positive frequencies, what is the value of signal function?
1.
And for negative frequencies, what is the value of signal function?
Minus 1.
Minus 1.
Minus 1. Now, accepted this definition.
Yes, sir.
Positive frequencies, you'll get minus j because signal function becomes 1. And negative frequencies, the phase
Yes.
shift should be pi by 2. That's why you get plus j. And this signal function for negative frequencies becomes minus 1.
Minus.
That is why you get a plus j. Okay. So that is how we got a single definition for h of omega. Once I get h of t from this, then you can directly write the expression for the Hilbert transform. So to get h of t, what I am doing is, because signal function is a well-known function whose Fourier transform is already known. Can anyone tell me signal function Fourier transform? I think you don't remember. I know. It is 2 by j omega. Am I right or wrong?
Yes, Yes, sir. sir.
Okay. Now here, signal function, is it in time domain or frequency domain? Here,
Frequency.
frequency domain. It is not in time domain. So I can't directly use this result of Fourier transform. So I need to use a property called as duality property. Duality property in Fourier transform. What is that property? excuse me, if x of t is having a spectrum of x of omega, please refer your notes once. Then capital X of t, can you see this property in your book? Duality or symmetry?
Yes, sir.
Fourier transform will be, can you please tell me result?
2 pi f of minus omega.
Small f, okay? I am writing it as small x of minus omega. So here, small x in time domain, I am writing capital X in frequency domain. Now capital X in time domain will lead to 2 pi times small x of minus omega in frequency domain. Just rewriting this again for our example. Fourier transform x of omega. Now in place of this I am writing signum function. So what is small x here? What is small x?
Sin t. Sin, signum of t.
Signum function, right? And what is x of omega here?
2 by j omega.
Nice. Now, can you write capital X of t? Can you write capital X of t? If x of omega is 2 by j omega, what is x of capital X of t? X of omega is 2 by j omega. I am asking you what is capital X of t?
2 by j t.
That's it. 2 by jt. Replace the variable. That's it. Okay. So this becomes 2 by jt. Right. Now tell me 2 pi is a constant. What is small x?
Signum of t.
Signum of t.
So small x is signum of t. I am asking you small x of minus omega. What is that?
Signum of minus omega.
Signum of minus omega. Now you have to tell me, is that signum function even function or odd function?
Odd.
Odd. Signum function is odd function. So if signum function is odd function, then what can I write this? Minus signum function of omega. Am I right?
Yes, sir. Yes, sir.
So what is now x of minus omega? It is minus signum function of omega. Okay. So now, since you have 2 on both sides, I'm removing that 2 because it is a constant. So I'm writing 1 by jt Fourier transform is minus pi signum function of omega. Clear?
Yes, sir.
Right. Now, going back to the actual transform. Do you observe here minus j signum function of omega or minus pi signum function of omega? Here, for Hilbert transform.
Minus j.
Minus j signum function of omega, not minus pi. So what will I do now? I will divide with pi on both sides. Okay.
Yes, sir.
So dividing with pi, what you will get? 1 by j pi t. Fourier transform will be minus signum function of omega. Accepted?
Yes, sir.
Right. But still this is not the correct one. What we need?
J. Minus j.
J, extra j is needed. So what will I do? I'll multiply with the j on both sides. Then tell me the final result. Minus j signum function of omega you have got towards the frequency domain. Now what is the time domain function?
1 by pi t. By pi t.
Right. 1 by pi t. Now If I say this as h of omega, now what will be this?
H of t.
H of t. So this h of omega is a transfer function of Hilbert transformer. Now what is this?
Impulse response.
Impulse response of Hilbert transform. The toughest part of this derivation is complete now. Okay, so let me recollect once again. Hilbert transformer is basically a phase shifter by an amount of plus or minus pi by 2. And to understand this Hilbert transform, and you can even check later that it is an LTI system. And for an LTI system, output is obtained as convolution between input and the impulse response. So that's x of t can be any other signal, but the Hilbert transformed version is always a phase shifted version. So we have to find the impulse response of the phase shifter. That is a Hilbert transform. So to understand that phase shift, I have explained all this in the frequency domain and made you sure that h of omega is taking the definition of e power of plus or minus j pi. And this is how we have written the definition for h of omega. And since I need the impulse response of the Hilbert transform, what I did is I got a single definition for h of omega, and by having some previous knowledge that signum function of t is having a Fourier transform of 2 by j omega, by applying the duality property, I have got the inverse Fourier transform of minus j signum function of omega, which is now representing the impulse response of Hilbert transform. So now, output y of t of Hilbert transform. How we are representing Hilbert transform? It is x cap, okay? Is convolution between x of t and the impulse response. Now tell me what is impulse response here of the Hilbert transform?
1 by pi t.
1 by pi t. So impulse response. So here for Hilbert transform, the impulse response h of t is 1 by pi t. Simply go for substituting this h of t in the convolution formula. That's it. That leads to your formula of Hilbert transform. So x cap of t equal to Hilbert transform of x of t, which is equal to x of t convolution h of t. Formula minus infinity infinite x of tau h of t minus tau dt. Tell me now, what is x cap finally? Integral infinite limits x of tau h of, in place of h of t, wherever you have t, you have to replace it t minus tau. Tell me, what should I write? Am I right what I wrote?
Yes, sir.
Okay. Now, just rewriting this properly. The Hilbert transform result is 1 by pi is a constant. I'm writing outside 1 by pi. Infinite limits over the integral x of tau by t minus tau t. That's it. This is the form. Got it?
Yes, sir.
Okay. We will conclude this session by seeing some 3 important points of Hilbert transform. And these 3 points I will ask you in the form of question. Okay? 3 important points. You can treat them as the properties of Hilbert transform. Now, the first question. X of t and x cap of t, that is the Hilbert transform, do their magnitude response differ or equal?
They remain same.
Yes. You observe that? Here I have shown. This is before phase shifting. This is after phase shifting. You observe that magnitude remains the same, only the shift in phase. That means either the signal x of t or its Hilbert transform will have the same magnitude response. So x of first point is x of t and its Hilbert transform x cap of t will have same magnitude response. Clear? Is it okay?
Yes, sir.
Yes, done. Next question. Next question I will be writing here. For a signal x of t, I have applied the Hilbert transform and you got x cap of t, which is a phase shifted version of x. First, suppose if I again apply the Hilbert transform for this result, what is the result? Tell me. For x cap, if I apply the Hilbert transform, what will be the result?
The original signal.
Not at all.
Sir, once the phase shift is done by pi by 2, again if the Hilbert transform is applied,
I'm not saying that. See here. If this is, for suppose I am talking about positive frequencies, phase shift is minus pi by 2. Am I right? If I perform the Hilbert transform. Am I right or wrong?
yes, sir.
Yes, it is. And you will get some phase shifted version. And I again perform the same. Do you observe the phase shifting reversal operation is done?
No, sir, I
No,
understood.
right? Okay.
Oh,
So this is the minus 90 degrees phase shifted version. Here the result is minus pi phase shift. Got it?
yes, sir.
For suppose if I'm talking about omega less than 0, if I perform phase shift of pi by 2, then this is shifted by 90 degrees. Again I'm performing the same. That means the phase shift will be pi. Am I right?
Yes, sir.
Yes. That means the net result can be explained like this. For Hilbert transform, the frequency response is represented like this. Whereas the double Hilbert transform, what will be the double Hilbert transform? What will be the response, frequency response? E power of plus or minus j pi. Am I right?
Yes, sir.
Now, cos pi plus or minus j sine pi. What is sine pi? 0. Don't think. It is 0. And what is cos pi?
-1.
Yes, minus 1. So, now see, a signal x of t, which is having a spectrum of x of omega, is shifted in phase, right? And again, it is again shifted in phase. That means x of omega into e power of minus j pi. So, Hilbert transform, again Hilbert transform. What is e power of plus or minus j pi value? Minus 1.
-2.
So that means this is minus x of omega. Am I right?
Yes, sir.
Got it? Okay. So if I again apply the inverse Fourier transform, you will get minus x of t. Am I right?
Yes, sir.
So now the second important one comes in. If I apply the Hilbert transform, maybe I can rewrite it again. If Hilbert transform is applied for x cap of t, what is the result? The result is minus x of t. Accepted?
Yes, sir.
Right. And the last property, one more question. Last, very easy. This is very easy. Tell me now, x of t and x cap of t, are these signals mutually orthogonal or not?
Yes, sir.
Yes, it is. It is yes directly because x cap of t is a
Phase shifted.
plus or minus phase shifted version
Yes, sir.
of x of t. Okay, so these two signals are mutually orthogonal. So you can write that here as a third point. X of t and its Hilbert transform x cap of t are mutually orthogonal. Clear this point? These 3 points?
Yes, sir.
Okay. And if they are mutually orthogonal, can anyone tell me like what condition it satisfies? Final question.
Their dot product will.
Exactly. If the two signals F1 and F2 are mutually orthogonal, that means it should be equal to 0. Okay. So T1 to T2, or I can write, you can even write from minus infinity to infinite, x of t and its Hilbert transform, the dot product should be equal to 0 because they are orthogonal. Okay.
Yes, sir.
Right.